we would like to be able to describe mathematically the velocity of an object from the point of view of another moving object. We call this relative velocity. So suppose here we've got the Earth at rest in the center of this reference frame, and here's the moon as seen from the Earth. So this red position vector here, RME, indicates the position of the moon from the Earth's point of view, or the position of the moon relative to the Earth. Here's the convention that we use for our subscripts. A subscript ME, M is first, E is second. This means of the moon from the Earth's point of view, or we also say of the moon relative to the Earth. These mean the same thing. So from the Earth's point of view, the moon moves on a very nearly circular path orbiting around the Earth. And so at any given time, we can show the velocity vector of the moon with respect to the Earth, VME, the velocity of the moon from the Earth's point of view. So at this moment, the moon would be moving with a velocity pointed in that direction. Later in the orbit, the moon could be over here, moving with this velocity relative to the Earth. Then later it's over here. So that's the velocity of the moon from the Earth's point of view. But the Earth is not the only point of view we could adopt. Here, I've picked a different reference frame with the sun at rest at the center of this reference frame. And then here is the Earth orbiting around the sun. The Earth's path I have in blue, sketched in blue, as a very nearly circular, actually it's elliptical, orbit around the sun. So the Earth is moving around the sun at the same time that here's the moon moving around the Earth. So as the Earth goes around the sun, the moon orbits around the Earth. So the moon ends up tracing out this green spiraling path around the sun. The moon is going around the Earth again and again as the Earth itself carries it around the sun. So in red, I've got the position vector indicating the position of the moon with respect to the sun, MS, the moon's position from the sun's point of view. And then at any given point on that green path, I can indicate the velocity of the moon from the sun's point of view. And we know our velocity vector is always tangent to our path. So here's VMS at this moment. The moon is going through this little loop, and then here's its velocity with respect to the sun at a later time. And one of those little loops, that would be when, let's say right here at that instant, from the sun's point of view, it looks like the moon has kind of reversed direction temporarily and is going backwards. We would say that from the sun's point of view, the moon is in retrograde right here, sort of reversing itself temporarily before swinging back forward. So the velocity of the moon from the sun's point of view is a much more complicated thing than the velocity of the moon from the Earth's point of view. And we would like to be able to relate these two things. How does the velocity of the moon relative to the Earth relate to the velocity of the moon relative to the sun? Okay, here's how we'll do it. We'll start by indicating their relative positions. So here again is a reference frame with the sun at rest at the origin, and here is the Earth, and here is the moon. So I've got multiple position vectors indicated. This vector indicates the position of the Earth relative to the sun. This vector indicates the position of the moon relative to the sun. And then this one indicates the position of the moon relative to the Earth. Note that when we say relative to, the object that it is relative to, that's at the tail of the vector. Relative to the Earth means the tail of the vector is at the Earth. So we see that we've got three vectors that look like they're arranged in a way that suggests the head-to-tail method of adding vectors. When we have a chain of vectors chained up head to tail, then the sum of those vectors is a new vector that points from the very beginning of the chain to the very end of the chain. So these two vectors here are sort of chained up head to tail. The position of the Earth with respect to the sun, plus the position of the moon with respect to the Earth, those two ought to add up to give us a vector that points from the beginning of that chain to the end of that chain. which is what we're calling the position of the moon with respect to the sun. So we've got this equation here representing this sum of vectors. This vector plus that vector gives us that vector. So this is all in terms of the Earth, Moon, and Sun, but more generically, if we have three objects, A, B, and C, then we would write this as our general relative position equation. The position of A relative to C equals the position of A relative to B plus the position of B relative to C. So that's a lot of subscripts to keep straight. Here's how I recommend you keep them straight. Note that B, which would be in this case like the Earth, E, that would be the Earth here and here, the Earth here and here. It's object B, one of the moving things. The B subscript appears on the inside, and the AC subscripts appear on the outside here. The A and the C would be like the moon and the sun. The moon and the sun, the outside subscripts. So A and C on the outside match A and C on the outside, and the B's on the inside have to match. So that's just how to relate their positions, but what we really want to relate is their velocities. So note, what if the Earth and or the moon move a little bit? If the moon moves a little bit and the Earth moves a little bit, then all three of these vectors will change. So some small change in this vector will result if there's a small change in this vector plus a small change in that vector. And I'm indicating that here. DRAC, D as an infinitesimal delta, a tiny change in this vector is the result of a tiny change in this vector plus a tiny change in that vector. And if I look at the rates of change of those three vectors, so divide those infinitesimal changes by dt's, then the rate of change of this vector equals the rate of change of that vector plus the rate of change of this vector. And by rate of change of a position vector, we mean velocities. So here we have it. This is telling us that this is the definition of the velocity of A with respect to C. That's equal to the velocity of A with respect to B plus the velocity of B with respect to C. And this again represents a three-vector triangle of additions. So this picture visually represents this equation here. The velocity of A with respect to B plus the velocity of B with respect to C. This chain of those two lined up head to tail, those summed up gives us a result that points from the beginning of the chain to the end of the chain. So that is this VAC right here. Once again, comparing this picture, this generic picture with ABC, back to our original example with S, E, and M, the sun, earth, and the moon. By identifying subscripts, we get this here. This is what we were looking for at the beginning. The equation that relates the velocity of the moon from the sun's point of view. That can be found if we know the velocity of the earth from the sun's point of view, if we know how the earth is moving around the sun, and we add to that the velocity of the moon from the earth's point of view, so how the moon is moving from the point of view of the earth, add those together, and we'll get this spiral behavior here. The resulting velocity of the moon, that's complex velocity of the moon with the retrogrades and everything, from the sun's point of view.